Hello and welcome to the last week of school for this school year. We've got a little bit to talk about still on the periodic table and what it can teach us, and we're going to look at that topic today. I'm going to swap us over to Schoology to make sure that I show you where everything is, and then we will introduce this last topic. So here we are. Don't forget, so we've got all of the events coming up here. It's a Sunday, so these are still coming in. Just as a reminder, all of this work can be turned in at any time up until the end of the school year because I'm not assessing any late fees. So you can turn these in. When I find it, I will put it into the gradebook as though it were on time. So even if you're behind, you still got a chance to catch up. Just put hard work into it. We've got the office hours listed here, and when you click them, it's got the information, so you can join. These are pop-in. If you want some help during these times, I'm on for an hour, just sitting here waiting for students. So I'll be doing something else, but essentially just waiting for students. And when you pop in, I let you into the meeting and we can chat for a couple minutes and hopefully get you straightened out with whatever questions you have, and then put you back on your way. We'll actually have a couple more assignments that I'm adding later this week. All of these are pretty short ones. So there should be no trouble finishing up this week's work in a timely fashion. Of course, here's our schedule. You can always click on this to see the weekly schedule here, and I will be filling this out shortly, forgot to. We've got the weekly schedule, which you were emailed, and then all of our work will be in the atoms and periodic table. So as an introduction here, remember in our periodic table, which we can see here, there was a lot of information in here that we went through last week. But one thing that I mentioned that we didn't get is how many neutrons are in a sample, which is an important aspect, although not as important as many of the other things like the protons, the electrons, and how those electrons are arranged. The information is partially included in here, and we mentioned that. So if I'm looking at chromium here, it's got an atomic number of 24, meaning it has 24 protons, and if it's neutral, it also has 24 electrons. And then its average mass, or what we call the atomic weight or atomic mass, is 52.00. But that is an average because, as we saw in our simulation here, I can build the same atom. Let's say that I make an atom of, let's do beryllium. I'm going to show if it's stable or unstable. Now, this is an atom of beryllium. It just happens to be unstable, so we wouldn't find it naturally too much. If it would be radioactive, so over time it would decay. Now, if that time is very, very long, there's still probably some on Earth. We see that with many of the radioactive elements that we find, like uranium that we use to power nuclear power plants, for example. This is beryllium. It's just not stable. And I can make it stable by adding neutrons. If I add 1 in here, it's still unstable. It is still a version of beryllium. This one happens to have, of course, 4 protons because that's what beryllium has, and 1 neutron. I should say, if I take that out, beryllium, this would be called beryllium-4 because the 4 refers to how many total protons and neutrons does it have. I could add another neutron, making it beryllium-5, still unstable. I could add another, making it beryllium-6, beryllium-7, beryllium-8, beryllium-9, finally stable. We've seen versions here in this simulator of beryllium. They just weren't stable until we got to beryllium-9, which means 4 protons because it's beryllium and 5 neutrons. Now we can keep adding these to find other isotopes. And if we had just 1 more, it becomes unstable again. So beryllium doesn't have very many stable options, although we might still find some of them in nature. So this would be what, beryllium 10, because it's got 4 protons, 6 neutrons. Now all of these would be found in the same place in the periodic table. They're all beryllium. And so in that regard, they are essentially all the same as far as chemistry goes. But this nucleus is different each time. And that's going to be the topic that we're going to wrap up with here. So I'm going to go on and share this guy. And I've got a new periodic table to show you. I'll make sure to show you where that is after I'm done on this page. Oops. Here is a new look at the periodic table. It's a pretty dense image, which is why it took a while to load there. But it's high resolution, so when you bring it up on your screen, you can zoom into it quite a bit. And so let's look at that beryllium right here. This periodic table is special because it does tell us the things that we were looking at before, but it adds some more information. Down at the bottom of each tile, so let's look at our beryllium here. It tells us very precisely the atomic mass, and this is an average. The last number in parentheses is an estimated value. The rest are known very well. So, but this is an average. So if we got a really big sampling of it, this would be what we'd measure. That's its atomic mass. But what else it does is it tells us the various mass numbers, which is right here. And a mass number tells us the number of protons plus the number of neutrons. Remember that our abbreviation for protons was P plus, and our abbreviation for neutrons was N0, N naught. So in this case, this is telling us that if we had a sample of beryllium, pretty much all of it would be beryllium 9. We would write that like this as an abbreviation, or the way we're going to be writing it is spelling it out fully, like so. That's a Y there. And this 9 tells us, of course, beryllium already has the information in it. That means 4 protons. The beryllium 9 means that its total mass number is 9. So 4 protons and whatever is left over, 5 neutrons. We can do this for any of these on this periodic table. So if I go over to the other side, let it catch up with me. Let's look at boron. Boron has 2 varieties that we would find in nature, boron 10 and boron 11. So let's summarize those up here. Boron-10, that means since it's boron, it would have 5 protons. And with the 10, the difference between 10 and 5 neutrons. But there's another variety that we would see an even greater abundance, even more of it in a sample, and that is boron 11, which means 5 protons. Boron always has 5 protons, and 6 neutrons. And there is a legend up here. It's got more information than you need to know, but there are some interesting points about it. Notice as we look through this periodic table, if we go down to zinc here, each of these different varieties of zinc has its own little slice of the pie, and that shows the various varieties that we would find in a sample. The coloration doesn't mean anything of the different slices. That's just to keep them separate from one another. But they do have a relative piece of the pie that tells us their abundance compared to the other types. So in the case of zinc, the most abundant, the most common is this zinc 64, which zinc has 30 protons. So zinc 64 would have 30 protons and 34 neutrons. There's more information in here too. You feel free to read this big paragraph over on the side, the background color key, because that can be interesting stuff. What I want to highlight here is any red numbers that we see. So let's look at selenium here. Selenium, if we dig up a big sample of this and measure all the different parts, the most common variety would be selenium 80, followed by selenium 78. Those are the about 75% it looks like. But we'd also find varieties of 74, selenium 74, 76, and 77. All of those are fine. All of those are natural, as is selenium 82. But notice that that is red. And up here in our legend, wait for it, right there, it says that red indicates the isotope is radioactive, meaning that although that 82 would be natural, it would also be radioactive. And that's just the number, the color of the number that tells us. That also brings us back to that term isotope, which if you'll remember from one of the videos from last week means, in Greek, iso of course means same. You know that from math, isosceles and so forth means a triangle with two legs the same. And tope is used in words like topography, and that means place. So we call these isotopes because we find them in the same place of the periodic table. All of these different varieties of selenium are isotopes. Now there could be other natural varieties that occur. Sorry, there could be other varieties occur, but in this case they are not natural. They would almost certainly be radioactive. So if I were looking at selenium and I wanted to know which isotopes are natural and stable, meaning not radioactive, that would be any of them here in black. And that would just mean that selenium has 5 different varieties, 5 different isotopes that are stable, will last pretty much forever, will not break down like that, of their own natural causes, and probably never. And there is another one that is natural, number 82, that is radioactive. So over time, there will be less and less and less of it as it breaks down. On your homework, you have 3 questions that I want you to be able to answer. I want you to be able to take a number like this 76 of selenium, and say, if you get selenium 76, how many neutrons does it have? Well, this is the number, 76 is the number of protons and neutrons. So you'd take the 76 minus the 34 that you know is protons, and you would get 42 neutrons in that particular isotope. I want you to be able to tell me if you are given a germanium that has 38 neutrons in it, what do you call it? Well, you would call it germanium 70, and you type that out just like that. And that is about all there is to it. I did want to go back and show you this again. So I will get out of this one. I can share myself here. Go back to the browser. And right here is our new periodic table. So I would suggest right-click on that, open the link in the new tab, and that will put it up here. You'll be able to see it. It is a dense file, so you might want to zoom in even more. The easiest way to do that, I'll see what I can do here in Schoology, but if you right-click on this and say, open image, a new tab, it will be even better. Oh, it wants you to save it. If you save it, you'll be able to see it for sure. Right here, it's a little hard to zoom in. to see, but you can zoom in. All I did was I'm holding control down and then I'm doing this, but then I have to move this around. So, but it does work that way, and you can see this much better. You are also welcome to print this out. That's what I did when I was writing stuff up. Okay, so that tells us a lot about what the isotopes are. We're going to take a little look at the arithmetic that goes into figuring those out later on, and we should begin.